Dark Snow Project is an international, collaborative, crowdsourced climate communication effort. We take scientists and communicators, usually to Greenland, to find new ways to tell that story. So we just started fundraising for this current field season, so fingers crossed we'll be going back again. This was actually the first season in 2013. That's my colleague, Dr. Jason Box. We had a knockout experience that first year, and it's only gotten better. I also do this video series called This Is Not Cool through Yale Climate Connections. But let's jump right into it. This is the key sentence that scientists of persuasion, people who study persuasion, tell us that people have to understand. Based on the evidence, 97% of climate scientists agree that human-caused climate change is happening now, but only a small percentage of Americans actually understand that, and that's one of the key problems. So racing through it here, it is physics. Most of you know we are burning coal, oil, and gas, and so we are emitting heat-trapping gases to the atmosphere, primarily carbon dioxide, also methane and a few others. And we can measure the effects of this as the sun radiation comes in and heats the earth. We have satellites that can measure that. And we can measure the heat that is re-emitted from the earth because, again, we have satellites that do a really good job of that. And some of it is getting trapped. That amount that is getting trapped is more now than it was 100 or 150 years ago. And the amount is not small. It is equivalent to about 400,000 Hiroshima-sized nuclear bombs every day, mostly going into the ocean. It is an absolutely staggering amount of heat. So it is not trivial. It is not a natural cycle that we're seeing. This is one of the key questions that comes up. Hasn't the planet changed before? And most people are aware that we've had ice ages going back many thousands of years. 20,000 years ago, this building would have been covered with a mile of ice. And the planet was cooler by only about 3 or 4 degrees centigrade. So it doesn't take very many degrees over the whole planet to change things in a really dramatic way. But we know why these cycles have happened, and in regard to the ice ages, changes in the planet's orientation as it spins on its axis. You might have heard the word precession. So the North Star that we have today will not be our North Star 5,000 years from now, because we're like a big top. If you spin a top on a table and it kind of does this kind of thing, that is precession, and that is a 22,000-year cycle. And then we also have changes in the shape of the Earth's orbit around the sun. Sometimes a little more egg-shaped, sometimes a little more circular, and that is, there is a 100,000-year cycle and a 400,000-year cycle. So that's happening. And then we have changes in the actual degree of tilt as the Earth spins on its axis. Sometimes about 22 degrees, sometimes more like 24.5 degrees, and that is a 41,000-year cycle. And long story short, when you graph these cycles out, because some people make it their business to do so, they're lining up pretty well with how much solar energy is hitting right around the Arctic Circle. And that is the determinant as to bringing us into and out of these ice ages. And the way these are lining up right now is that we should be, over a very, very, very long term, cooling, but we're not. All things being equal, if humans weren't here sometime in the next 10 or 20,000 years, we might go into another ice age, but as things stand, it's going to be anything but that. We know it's not the sun. We have really good measurements of what's coming out of the sun, particularly in the last 40, 50 years. The first part of the 20th century, solar energy was increasing a little bit, but it's been flat or declining since about the 1960s. This is a graph from Judith Lean at the U.S. Naval Observatory. She's very clear on this. Now here's something that we've probably all been running into, especially you folks, in the last several months, because we're seeing extremes in weather. But extremes that come in the summertime can be extremes of rain or heat or drought. When they come in the wintertime, they can be snow. They can be big storms. This is a little hard for some people to kind of square with the idea that the planet is warming. But the planet is warming. And so here's the thermometer readings going back about 150 or so years. And these are all the major temperature data sets. They're all very much in accord. The reason it goes back that particular length is because that's the span in which we have good thermometer records. And generally, we don't argue with thermometers. This is a thermometer. It's the old-fashioned kind. It's actually got a fluid in it, right? And we all learned how these work in 5th grade. If you add heat to the fluid, what happens? It expands, of course. And so it expands, and it rises up the tube, and then we can read an increase in temperature. And it expands because that is a fundamental principle of the way the universe is built. Okay, we know that from 300 years of physics. So this is a thermometer. If you think about it, it is a known amount of fluid inside a vessel of a known volume. And if we're adding heat to it, and most of that heat, that 400,000 nuclear bombs a day, is going into the ocean. And so we should expect the ocean to expand, of course. So here's sea level for the last 2,000 years. So, and if you want to pull in on it a little bit for the last 24, 25 years, this is the very accurate satellite measure of sea level from the University of Colorado, which you can look up anytime, just Google it, Colorado Sea Level Satellite. What we can say is, based on everything we know about physics, there's no way that you get this kind of a graph in the absence of a warming planet. So we can all agree, the scientists say it is unequivocal that we are warming. This is just something that we simply know. We also know from literally tens of thousands of other types of phenomena, like shrinking Arctic sea ice. So Arctic sea ice has been behaving much as we might predict. As the planet warms, it is going away. And here is the basis of the story. Because if we look down at the North Pole and we see winds around the planet here, this is the jet stream, okay? And what drives the jet stream is the temperature difference between the Arctic cold and the temperate zone. The jet stream drives weather around the planet. So you think of me as the weatherman, you see the weatherman standing in front of his weather map, and the fronts are coming across like this. What is steering those fronts is the jet stream. As there is less ice up here, there are big swaths the size of Texas, the size of California, and larger, that used to be completely covered with thick, thick ice. Now that's gone. It's open water. So instead of temperatures that could plunge way, way, way below freezing, now you've got temperatures that are at least 32 Fahrenheit, 0 degrees C, and up, which is a big, big, big change. And there's a lot less of a driver for the jet stream. And so the jet stream, we have observations now, is starting to slow down, is starting to meander like a big river, and you get these big troughs and then peaks that go way up into the north. And this has started to affect our extremes in weather that we're seeing. A lot of you will remember spring of 2012, where we had 3 weeks of like 80, 90 degree weather here in the eastern United States. We were setting unbelievable records, just thousands and thousands of records for warm temperatures. And that's because the jet stream was dipping down and they were getting record snowfalls in the southwest at the same time, while we were getting this heat here. And this big meander in the jet stream just stuck there for about 3 weeks, and that's what caused that. We've also seen kind of the opposite effect. If you remember the polar vortex winters of 2013, 2014, where we had a big, big peak in the jet stream up around Alaska that was drawing unusual warmth up there, and then dropping this big blob of cold air down on top of us here in the east. What we have seen over the last several months is a pattern that looks an awful lot like this.
We're in the middle of something called the bomb cyclone weather event. Not clear you come up with that name or what it means, but here we are. It sent temperatures plunging all over this country. The severe cold has prompted assertions that it is the product of global warming.
Tonight, more than 200 million Americans dealing with an Arctic blast. Winter weather alerts from the Rockies to New England, even into the deep south.
Well, it doesn't look or feel at all like January around 8 grade.
There's a lot of lawns. You can see out there
they're not covered up by the snow.
Currently, we are below our average snowfall by more than 2 feet, which makes sledding and skiing a little difficult.
The climate in the Arctic affects the climate outside of the Arctic.
The Arctic is warming at twice the rate of the temperate areas of our planet.
When I started my career in the Arctic in 1981, 85% of the Arctic basin was covered with multi-year sea ice, which is this stuff that survives the summer and grows the next year, and is very thick and hard. Well, now only about 12% of it is multi-year sea ice.
The thick multi-year sea ice has now transitioned to thinner first-year ice. So it's gone from like 10 feet to 2 or 3 feet and is much more mobile.
The sea ice dynamics in themselves have impacts that go far beyond just the ocean, so to say, where the sea ice is.
There are signs of a connection between the Arctic and the rest of the world.
Those connections, teleconnections, as they are sometimes called, should be studied further.
There's what we would call an emerging signal, an association between the loss of sea ice and the warming of the Arctic and the frequency of severe weather events, especially during the winter season in mid-latitudes, in particular eastern North America and eastern Asia.
You have this big heating in the Arctic area.
And that causes the polar vortex, which is a byproduct of the high pressure pattern over top of the pole. It's causing that to break down because you've got a lot more heat coming from the ocean up into the atmosphere.
That essentially changes like the jet stream. It causes the jet stream to kind of do dips farther down.
The polar vortex is the jet stream.
Whenever you see big storms coming or heat waves, if you look at the jet stream, you'll see these big dips.
What happens basically with the polar vortex is you get a lot more lobed structure to it, and those lobes penetrate down far over top of the planet towards more temperate latitudes. If you're on the outside of one of those lobes, there's a tendency to draw up warm air much further into the Arctic than you would have otherwise. And if you're on one of the cold sides, you'll draw down cold air down into that lobe on the other side.
And so you get more extreme heat waves, more extreme storms, more extreme cold.
And so people in the southern states, for instance, will go, man, I'm in southern Florida and it's like freezing cold here in February. It's supposed to be warmer than this.
This was the first freeze that Orlando has had in nearly 4 years.
Well, you're sitting underneath that lobe that is drawing that cold air down from the planet. Some people will be sitting up in Alaska at the same time and say, wow, it's way warmer up here than it used to be. And it's because that warm air is penetrating much further north.
It is too warm in rural Alaska. In the state's southwestern region, high temperatures of 10 to 20 degrees above average are affecting everything from recreation to survival.
So there's lots of evidence that the loss of ice north of western Russia blocks the jet stream and allows colder air to reach into eastern Asia.
A similar thing happens in the eastern United States in the sense that the sea ice loss north of Alaska is fairly pronounced, especially in the summer and autumn. That tends to build up this upper air ridge in the early part of the winter, even into midwinter, and that in turn leads to a downstream impact, which is the northwest to southeast flow that reaches the Midwest and the eastern third of the U.S.
These are events that have happened in the past, but they are happening more frequently now. The real discussion among scientists is not whether climate change is happening or whether we are responsible for it. The question that's being asked, is this the action of the Arctic ice? How much of a component could there be from warming in the tropics? And so they're having arguments about some of the internal dynamics that we're seeing play out. But the overall picture of climate change is absolutely clear. There is a current in the ocean, and it distributes heat from the depths of the ocean to the surface and then around the whole planet from pole to pole, from equator to pole. That current, because the way it distributes heat around the planet, it is responsible for what we think of as the normal climate of the planet. But that current has not always been exactly as it is today. And there are a number of scientists that are looking at the changes we're making, and we're changing the temperature and the salinity profile of the North Atlantic. That is one of the major drivers of that global current. And so the question is, could we be pushing ourselves into a situation where that flow begins to destabilize? No one is predicting that that is going to happen imminently, but we are seeing signs, if you've been reading the Washington Post over the last month or so, recent studies by Stefan Rahmstorf, among others, showing that there is some kind of a slowing happening in that current in the North Atlantic. Now, I was up in Greenland last summer, and I had a chance to talk to one of the great ice core specialists on the planet, J.P. Stephenson. So he has looked back through time by looking at the layers in the ice core to learn about, well, one of the things he's learned about is how that flow has changed over time. And this is one of his major concerns about where we're going with climate change. So this is a relatively short video, but I think it's a potent one and one that we should pay attention to.
The last 11,000 years, that's since the Ice Age, this our interglacial period has been unreasonably stable. And we don't know why. With an enhanced greenhouse effect from burning of fossil fuel, CO2 and methane and so on, you would have a gradual increase in temperature. That's what all the models show you. It's sort of a gradual increase in temperature. But that's assuming that the climate plays nice. And we actually know from the ice cores that the climate does not play nice all the time. Right now, by emitting greenhouse gases, we are doing the same with the climate system as the investment banks in the US did when they were selling subprime loans in the economy in 2006 and 2007. In the last million years, there's been a cycle of approximately 10 ice ages. And they were sort of around 90,000 years long, each of them. And then there was an interglacial period separating the ice ages of about 10,000 years. That's sort of the standard rule of events in the last million years. If we then zoom in on an ice age, you see that inside an ice age, the climate is extremely unstable. And you have this sequence of abrupt climate changes that happen basically from one year to the next. And it swings from semi-cold to very cold, semi-cold to very cold, within very short spaces of time. But each of these cycles is about a couple of thousand years long. And we had that 26 times in the last ice age. All the big cultures in India, China, Mesopotamia, Egypt, South America, all came after the ice age. So we are assuming that this is the standard. Our collective memory refers to this as this is normal. And maybe by enhancing our emissions of greenhouse gases, we are actually tipping the climate system to become yet unstable again as it used to be. We can face a climate change that happens just as sudden as a financial crisis. We have tons of examples of climate changes where we see complete reorganization of the atmospheric circulation from one year to the next. And that will be extremely hurtful for any agricultural activity in the world, because the weather will change and will not change back. Fast climate transitions, these abrupt climate changes that we see recorded in the Ice Age, they were discovered in the Greenland ice cores. But now they keep finding them everywhere in the marine sediments wherever they look. But when it comes to Antarctica and the Southern Ocean, you don't see them. What you see there, it's also a wiggly climate line, but opposite. So when it's warm in Greenland, Antarctica cools off. And when it's cold in Greenland, Antarctica warms up. So these abrupt climate changes, it's an internal oscillation in the Earth climate system. What if what we do now is introducing so much fresh water into the North Atlantic that the North Atlantic current would sort of stop? That would make it terribly cold in Denmark, where I come from, because all of Northern Europe is placed at completely unreasonable latitudes. Just because we have the North Atlantic current, we have remote heating, so to say. If that's going to be switched off, we're getting very, very cold. But still the Earth could get warmer on average. It's just a distribution problem now. In principle, there's no reason why the Earth could not get warmer, but still Northern Europe and North America could get cold. Still, that area is not large compared to the global area. What we know from the sudden climate changes in the past is that these abrupt changes represent a reconfiguration of the entire atmospheric pattern. What if, with the emission of greenhouse gases, that we trigger a situation when this system all of a sudden goes into a feedback? If you reconfigure the transport patterns of high pressures and low pressure systems over North America and, for instance, Europe, but particularly North America and the Midwest, and all of a sudden it stops to rain, and it hits the Midwest and the US, and it leads to massive crop failure, that's going to impact the entire world. We don't know. We don't know what the threshold is, but we are rats inside the experiment.
When people tell me, you know, the Earth has changed before, so why should we be worried if it's changing now? I say, when I talk to the people who look into the distant past and know about the changes that have taken place in the past, those are the folks with their hair on fire about what we're doing because they understand the scale of the changes that are possible. One thing that I've learned in taking on the subject matter is that it is critical, if we're going to talk about it, that we don't just beat people up with what the potential impacts are. I want to talk about solutions because there's a huge story to tell, and this is where the light bulbs really start to come on when I show people how far we are towards having the solutions. In fact, we have all the solutions we need. It's just a matter of deployment at this point. I like this because it comes from the Financial Times, which is obviously not a lefty-leaning environmental rag of any kind. The long twilight of the big oil companies, following the Paris Agreement, where 199 countries, and we're still part of it, basically decided that the end of the fossil fuel age was coming. And based on what we know about how technology is changing, they're predicting the obsolescence of all fossil fuel production within the next few decades. It sounds impossible, but these are very conservative people who are making this prediction. There's a number of reasons why they think that. We're going to start generating electricity without releasing heat-trapping gases. So wind, solar, a little bit of geothermal, a little bit of tidal, a few other things, but wind is a huge success story right now. Scientific American, wind is one of the cheapest sources of electricity and getting cheaper. If you look back over a few decades, you see that the prices have continued to come down, and as they have come down, we have started to use more wind, just like Econ 101 would predict. You have a good that has a positive value and the price comes down, so you sell more of it. If we look at the cost of energy from some key representative sources, cost of electricity, wind is actually producing right now some of the cheapest electricity on the planet. Gas, pretty competitive, 48 to 78. Solar, moving up fast on the outside, and this is changing the environment. This is changing the landscape in a way that is so dramatic. You keep seeing the words disruptive, paradigm shift, you know, breathtaking in terms of trying to describe this change. Popular mechanics. Building a new wind farm costs less than running an old coal or a nuclear plant. The people that are closest to wind energy, Iowa, say wind power is saving Iowans on energy. They have a very large penetration of wind energy in Iowa, 35% or so and climbing, now adding a lot of solar as well. And their cost of electricity has come down about ½ cent per kilowatt hour in the last 20 years, while the rest of us are paying about ½ cent more on the average. So the places with lots of wind energy are doing pretty well. Des Moines Register agrees, and that's why companies like Apple, Facebook, Microsoft, and Google are flocking to Iowa to take advantage of what Tim Cook, the Apple CEO, says is a world-class power grid. And for Apple to set up a data center there, data centers require the highest possible quality of electricity in terms of stability, in terms of just rock-steady delivery of power. Google, Facebook have deals that let their data centers run completely on renewable energy. We're seeing more and more companies ask for 100% renewable energy. General Motors, Dow Chemical, something like 70% of the Fortune 100 companies now have renewable energy requirements that are very, very demanding. 80%, 100%. Here's Jeff Bezos christening the latest Amazon wind farm. Amazon has a 100% renewable energy goal. And again, they have data centers and they require very, very high quality of power. They want 100% renewable. And this is a beer commercial. This is not some kind of politically correct boutique kind of impulse among the Fortune 500 companies. A perfect example, the Kentucky Museum of Coal History now has solar panels on the roof because they did the numbers and that's what made the most sense, right? That's where we are right now. This is why they use words like disruptive. Big companies who have made big bets on fossil fuel, gas, natural gas in particular. Siemens is a huge company that has big investment making the turbines that go into natural gas generators, laying off thousands and thousands of people. Companies that generate power from oil and gas are cutting employment. Renewables are putting other forms of power generation under increasing pressure. You see the word disruption, unprecedented scope and speed. It's happening in Asia too. Mitsubishi Hitachi also laying people off. The dawn of renewable energy starting to pinch. Renewable energy exploding. And again, that's Econ 101 because the more we build things, the better we get at it, the more the price comes down. And this is a runaway train at this point. General Electric continuing to encounter difficulties as the impact of the clean energy revolution persists. General Electric's been in big trouble because they made a huge bet 3 or 4 years ago on natural gas turbines that they thought was going to carry them through the middle of the century, and it's crashing right now because of the pressure that is happening from renewables. They're shipping more megawatts of wind turbines, but it's facing pressure to lower prices because there's so much competition in that space. And because there is so much wind energy coming on, places like Texas are starting to see negative pricing in electricity because of the amount of electricity that is coming in from wind and increasingly from solar. So in San Antonio, Texas, the local utility there has a deal that if you can save your dishwashing and clothes drying till after 9 o'clock at night, the electricity is free. And that's because of wind energy. So we're seeing this more and more. Germany is familiar with this. Germany has had this happen something like 100 times just last year, where they're paying people to take the electricity from the grid, negative pricing. Now this isn't something that we want, that's ideal. It is an artifact of how rapidly we're bringing this energy on and how much we have to catch up with better transmission to take it away or storage to store it, which is a whole story in itself. And this is Senator Jeff Flake talking about a similar effect happening with solar energy increasingly in the American Southwest.
In Arizona these days, between the hours of 11 a.m. and 2 p.m., we get negatively priced electricity from California. There's so much solar being produced in California, they can't use it all. They push it to Arizona during those hours and pay our utilities to take it off the grid.
Negatively priced. So solar is the other emerging story, much more rapidly than anyone would have imagined 5 or certainly 10 years ago. Germany is the success story that a lot of people point to about solar. And so we've seen from some of the predictable quarters a lot of Germany bashing over the last 4 or 5 years. And I really like this clip from Fox and Friends.
What was Germany doing correct? Are they just a smaller country that made it more feasible?
They're a smaller country, and they've got lots of sun, right? They've got a lot more sun than we do.
Germany has a lot more sun than we do. Okay, so this kind of illustrates my point that, you know, we haven't been to war with Germany in a long time. Many people have forgotten where it is. As a public service, I like to remind people Germany is a cloudy northern European country on about the same latitude as Labrador, Canada. And if we look at the relative solar resource of Germany compared to the United States, red is a lot, green is still pretty darn good, blue and purple not so much. In fact, Germany has a poorer solar resource than Alaska. Alaska has a better solar resource than Germany, and yet they are leading the world because they have policies that make it so. And they decided to lead the world. But watch out, the UK is coming up fast. They have cut their carbon emissions below the level of the 90s. Not the 1990s, the 1890s. Yeah, that's how fast it's happening. We identify the UK as the birthplace of the coal revolution, the industrial revolution, and coal is simply dropping off the map there. And part of the reason is because the price for solar energy is just dropping like a stone. My scientist friends always tell me, don't just look at a graph and imagine that you see a trend where there might not be one. But I'm going to go out on a limb and say there is a very definite trend here, and we're only up to 2013, and it continues. We would have to like really blow that up to see how that continues to drop. Here's one I like to show. This is the largest, for now, the largest photovoltaic installation east of the Mississippi. It's not in Florida, it's not in South Carolina, it's in Lapeer, Michigan. They had their big opening in October. I found out later that 400 people showed up in the rain to get a look at this thing. Yeah, it's fantastically popular. California has set a goal for 50% renewable energy by 2030. They're going to make it by 2020, 10 years ahead of time. And what I tell people in the industrial Midwest is, these are your competitors. Germany, Denmark, California, Colorado, the states and the countries that have decided to move ahead and run their economy on energy that is free, or the fuel cost is free. How are you going to compete with them? You better decide, because they're not waiting. The gentleman asked a really great question in regard to what happens when the wind stops. And you can ask the same question about sun. Obviously, the sun goes down. This is a big deal. But what we hear is that solar and wind energy are so-called intermittent sources of energy, right? Sometimes they're there, sometimes they're not. Important to remember, all power sources are intermittent, okay? Example I like to give is during the bomb cyclone in January, the big nuclear plant, Pilgrim, up in Massachusetts, shut down instantaneously. Instantaneously went offline in the middle of the blizzard. But because all utilities have contingency plans for what happens if their power plants go offline, they simply filled in with reserve power, and nobody's lights went out, and everything worked out just fine, because this is what power engineers do, and they're really good at it. A coal plant is going to be offline, it's going to be down something like 44 days a year. And some of those outages will be scheduled, and some of them will be sudden and instantaneous. Same thing with nuclear plant, about 36 days a year, and then every 17 months you have to refuel it, and that's a 6-week process. And you have to plan for that. All power sources are intermittent. This is the important thing to understand. Engineers have dealt with this successfully for 100 years. With wind turbines, for instance, in an array of, say, 100 turbines, you might expect 1 or 2 to be down at any given time, but of course, the rest of them are still spinning. So they have a great deal of resiliency and redundancy. What I like to point out is that, as we have seen in a coal or a nuclear plant, you can be cooking along and then suddenly drop right off the map in a microsecond. So you can lose hundreds and hundreds of megawatts in the blink of an eye. With wind, for instance, what you have is a power source that comes and goes in kind of a gentle, predictable curve. So with wind energy, we can forecast, say, 24 hours ahead. Here's a forecast from France in 2011 versus actual. So forecast in blue, green is actual. What that gives your engineers is 24 hours notice of how much energy they're going to have and how they're going to meet the challenge and move their resources around to cover it. And here's the emerging wild card that nobody was expecting, even just a few years ago. This is a battery. You've all heard of Tesla motors. They can take those same batteries that they put in their cars and stand them up next to, say, a wind turbine or a solar array and store the energy. Now, Elon Musk did this in South Australia, basically on a bet. He got into a bet with some billionaire down there, and he said, I will set up a battery system for you down there in 100 days or it's free. And he did it. And what happened, the battery system went online on December 1st of this past year. And just a few weeks later, on the 14th, a giant coal plant nearby tripped off, and the battery stepped in a microsecond and smoothed things right out. So the company that purchased the battery is very, very happy because they were making almost $1 million a day during the time of that outage based on their battery. And so if people are making a lot of money on a technology, you can predict that many, many more competitors are going to start to get into that space. And that's what's happening. So the big utility in Colorado, Xcel, put out a request for proposals, and they've got literally hundreds of returns on it for proposals for wind, for solar, for wind and solar plus battery at prices that no one would have ever believed even a year or two ago. And if this holds, then what we're looking at is something that really blows everything else away in terms of the price of the power that's available with storage. Not to be Pollyanna about the problem, because the problem is real and the problem is big. We have the solutions, but we literally need to be deploying them 10 times as fast as we are to avoid the really terrible consequences of climate change. So people ask me, what can I do? What should I do in the face of this global crisis? And I used to talk about buying more efficient appliances and eating less meat and all the things that you think about if you're, an ecologically minded person. But what I tell people now is talk to somebody. Because all of the polling that we have tells us that most people in the country know that climate change is happening, and most of them are concerned about it because they know that we've got something to do with it. But they're not talking about it because they think they're all alone. They're not hearing it from their friends, from people at work, from people at school. And so they think that somehow they're isolated and they're the only ones that are worried. Talk to somebody.